Okay, in this video lecture, we are going to discuss why we can treat air at 310 kilopascal and 25 degrees Celsius as an ideal gas. Now, let's take a look at this condition first. 310 kilopascal, that's about 3 atmospheres. So that's roughly the typical pressure of air in a car's tire. If we talk about the gauge pressure, this would be about 2 atmospheres gauge pressure. And 25 degrees Celsius, that's the what you may call comfortable room temperature. It's a comfortable spring air temperature in the atmosphere. So this is very similar to what we consider ambient condition, slightly higher pressure than ambient condition. And this is air. We often, when we work with problems involving air in such a condition, we treat the air as ideal gas. And let's use quantitative evidence to justify that we can use the ideal gas equation of state properly for air in such a condition. We are going to use the concept of a compressibility factor. We're going to find the reduced pressure and the reduced temperature of air at this condition. And then we're going to use the generalized compressibility factor chart to find the corresponding compressibility factor for air at this condition and show that the compressibility factor is essentially 1, which tells us that the air at this condition is a very good approximate for the ideal gas. Okay, compressibility factor is defined as such. PV equals RT, and this is the ideal gas equation of state. But what if a gas is not an ideal gas? We need to make some correction. The correction we make is to use the generalized compressibility, compressibility factor. This is the compressibility factor. Okay, Z is the compressibility factor. So for an ideal gas, Z is equal to 1. If a gas whose Z is very, very close to 1, then that's a very good approximate to the ideal gas model. And in order to find the compressibility factor for a particular gas in a certain condition, we use the generalized compressibility factor chart, which is this chart. Okay. In this chart is generated using experimental data, and it involves many different substances. And by calculating the reduced pressure and the reduced temperature for these different experimental conditions, we can actually plot this generalized compressibility factor chart, which relates the Z, the compressibility factor, with the reduced pressure and the reduced temperature of a system. And reduced pressure P sub R is defined as the pressure of the system divided by the critical pressure of the pure substance that forms the system. Here we have a pressure of 310 kilopascal. And we can find the so-called critical pressure for air. If we see air as a pure substance, is actually an average critical pressure for the gas, the constituents that form the air, the mixture. If we look up the table from the Tango and Bowles textbook, table A-1 in the appendix, we'll find the critical pressure for air to be 3.77 megapascal, which is 3,770 kilopascal. And the reduced pressure is therefore approximately 0.08. Let's just use one significant digit. The reduced temperature is defined as the temperature of the system divided by the critical temperature of the pure substance that makes up the system. In this case, we have 25 degrees Celsius, which is 298 Kelvin, divided by the critical temperature of air, which is 132.5 Kelvin, and this is roughly 2.2. Let's use 2 significant digits. Okay, now these both quantities are dimensionless, so they have no units. And let's find out where they are, what location they represent on the generalized compressibility factor chart. The x-axis is reduced pressure, P sub r. The z-axis, the y-axis is the compressibility factor z itself. Each curve in this chart represent one constant T sub r value. The top curve, this curve, represents T sub r equals 2. And then the lower you go, the lower curves represent lower TR values. The bottom one represents T sub r equals 1. So we have a T sub r of 2.2, which means our T sub r should be a curve that's slightly above the T sub r equals 2 curve. And let's say it's this curve. Let's just say that it's the T sub r equals 2 curve. And our P sub r is 0.08, is very close to the 0 point. It's roughly here. Okay, this is, let's say this is a P sub r. P sub r equals 0.08. And here we find z approximately 1. So corresponding to this condition, P sub r equals 0.08 and T sub r equals 2.2, z is approximately 1. So air at this condition can be approximated, can be seen as a ideal gas. Because its compressibility factor is very, very close to 1. And now we have shown the reason behind the fact that we treat air at the ambient condition or room temperature, room conditions as ideal gas. And there's a reason, and we have shown this quantitatively using the compressibility factor of air at 310 kilopascal and 25 degrees Celsius.